Now we want to take a look at electron configuration. In our last discussion, we discussed how the electron cloud is divided into orbitals, and we've represented each one of those orbitals as a box here in this picture. And these orbitals were organized according to their energy into energy levels and sublevels. We name these energy levels using numbers 1, 2, 3, 4, 5, and we label the sublevels as letters S, P, D, and then F as well. Our goal now is for any given atom to know where all its electrons are located and what orbital each of those electrons are going to be located. Remember that definition of orbital that we've already met. An orbital isn't a flight path. It's just a probable location of where an electron is likely to hang out. So we want to know the hangouts of all the electrons in an atom. It's kind of like where the FBI in the old days where they were investigating the mob and they'd map where all the mobsters like to hang out. That's what we as chemists are attempting to do here. Let's quickly define some terms. First, electron configuration is a description of which orbitals are occupied by which electrons. Degenerate orbitals, or orbitals that have the same energy level, for example, the 3p orbitals all have the same energy. So they would be degenerate orbitals, orbitals that have the same energy. I'm going to define orbitals as having the same energy as not just do they have the same energy, but for our purposes that means the orbitals are in the same energy level and subshell. So they're degenerate orbitals, orbitals with the same energy. The next state is term to define is the ground state electron configuration. That's the electron configuration that has the lowest possible energy. Anything with the lowest possible energy is going to be favorable when it comes to the electron configuration. Then finally, perhaps the most funnest word to say in all of chemistry, the Aufbau principle. Go ahead, say it. You know you want to. Aufbau. The Aufbau principle are the rules we're going to use for determining an electron configuration. Without further ado, let's Aufbau it. The Aufbau principle consists of 3 rules. First, lower energy orbitals fill before higher energy orbitals. 2, an orbital can hold only 2 electrons. The 2 electrons in that orbital have to have opposite spins. This statement right here is also known as the Pauli exclusion principle. Only 2 electrons can occupy this. Only 2 electrons can occupy an orbital, and they have to have opposite spins. Third, if 2 or more degenerate orbitals are available, 1 electron goes in each until all are half full. The electrons in the half-filled orbitals all have the same value of their spin quantum number. This is known as Hund's rule. All right, let's apply each of these rules for determining the electron configuration of some atoms. Why don't you write down the word risk? Write down the word risk. R-I-S-K. Risk. R-I-S-K. Risk. The first part of the Aufbau principle tells us that we have to fill from low energy to high energy. So what is that energy relationship between the different orbitals and the different sublevels? Well, here it is. See? No problem remembering it, right? You look at it, you've got it nailed, right? Nah, don't worry about it. You need to memorize it, but you don't. Know why? Because on every single chemistry exam you'll ever take, somebody will attach the world's greatest cheat sheet for remembering the order of energy level and subshell filling. And that is, drum roll please, Your periodic table. It turns out that the periodic table was unknowingly, when it was created by Mendeleev, actually arranged in order of electron configuration. By looking at a periodic table, we can tell an element's electron configuration. First of all, let's start by remembering our row numbers. Remember, the periodic table's rows, or periods, are numbered 1, 2, 3, 4, 5, 6, 7. Going that way. The row turns out that the row number is the elements highest occupied energy level. But wait, there was more. Because our periodic table goes from 1 to 7 at the top, that means that the energy of our energy levels goes from 1 to 7, which is kind of a well-duh statement. We've kind of beat that one into the ground. But now we know the relationship between that and the periodic table. That the row number is the element's highest occupied energy level. So let's zoom in again here. Zoom, 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 zoom. All the elements in this row have the second energy level as their highest occupied energy level. All the elements in this row have the fifth energy level as their highest occupied energy level. All the elements in this row have the seventh energy level as their highest occupied energy level. So row number equals energy level. Columns tell us sublevels. Column 1A and 2A are what's known as the S block. All the elements in 1A and 2A, columns 1A and 2A, have their outermost electron Then if we leap across the Great Divide here to to 3A, 3A, 4A, 5A, 6A, 7A, 8A, all these elements in 3A through 8A are referred to as the P block. Then we have this sunken low portion of the periodic table here. This sunken low portion is referred to as the D block. And then these two orphan rows down here, these are the F block. Whoops. All the elements in the P block have their outermost electrons in the P sublevel. All the elements here have their outermost electrons in the D sublevel. All the elements over here have their outermost electrons in the F sublevels. So you need to have in your mind, when you look at the periodic table, you need to have memorized that the periodic table is really S, D, P, and F. Also, before I forget, and we'll talk about it here in a second, there's one element that's really misplaced. The element helium really belongs over here. It just puts on airs, boom, 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 and sometimes gets a little lightheaded, boom, 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 and thinks that it's a noble gas. And it is actually in terms of properties for reasons that we'll go into later. But electron configuration-wise, it belongs over in the 2A grouping. But chemical property-wise, it belongs to 8A. And we'll reconcile those facts here in a second. Let's look at some electron configurations. And when you look at configurations, let's start at the very beginning, because it's a very good place to start. When you do electron configurations, you begin with hydrogen, helium, and lithium. So let's take a look at hydrogen. Hydrogen is our first element, and hydrogen has one proton and one electron. So we only have to place one electron for hydrogen. So we need to find the lowest available energy spacing for that hydrogen. Well, if you can't remember the order of those energy fillings, you can use the periodic table to help you. Hydrogen is in the first row, so we know its energy level is going to be the first energy level. Hydrogen is also in the S block, so its outermost electron is going to be in the S sublevel. Hydrogen is in the first row of the S block, so it's going to have one electron. That's right. Something we haven't talked about is the number of columns you're into a block tells you the number of electrons that that element has in that block. Since hydrogen's in this first row here of the S block, it has one electron in the S block. Now, we would write hydrogen's helium's configuration just like I have here. This is known as a condensed electron configuration for hydrogen. When you do a condensed electron configuration, you write the energy level number first, then you write the sublevel right next to it, then you say the number of electrons in that sublevel. And you always write the number of electrons as a superscript, and that superscript always goes on the right-hand side. So that's hydrogen. What about helium? Helium is actually a misplaced element. Helium actually belongs right here. Helium has an atomic number of 2. So helium has 2 electrons that we need to find a home for. The first energy level has the S sublevel. The S sublevel has 1 orbital, and every orbital can hold 2 electrons. So helium would have 2 electrons, both in the 1s orbital. And we could tell that from the periodic table because it's in the first row, S block, and it's 2 into it, 1, 2. So it would have an electron configuration of 1s2. Let's keep the party going. Let's look at another element. Let's take a look at lithium. Lithium is our third element, so it has 3 electrons. What we're going to do to determine lithium's electron configuration is we're going to read the periodic table like a book. We're going to read it top to bottom, left to right. So, as we start reading towards lithium, at the top of the periodic table, we come to the first row. So we come to the first energy level, 1s. And there are two elements in the s block, and there are two elements in the s block because helium really belongs there. So 2 electrons in that s. Then we come to lithium in the second row, and lithium's in the s block, and it's 1 electron in it. So that's lithium's electron configuration. We would say that the electron configuration of lithium is 1s2, 2s1. Remember how many electrons that each sublevel can hold. We said in our last lecture the s sublevel can hold 2 electrons, the p can hold 6, the d 10, and the f 14. But the periodic table will help you with that too. Let's keep going. Let's look at beryllium. Beryllium is right here with 4 electrons. We read left to right, so we read through the first row, or the first period, 1s, 2. Then beryllium's in the second row, s block. So we know its outermost electrons are going to be in the 2s. And how many electrons is it going to have in that 2s? 1, 2. It's in the second row, so it's going to have, or second column, so it's going to have 2 electrons there. So its electron configuration would be 1s2, 2s2. All right, if we keep going, we get to boron. And for the first time, we're leaving the s block to deal with an element. Boron has 5 electrons. To get to boron, we read down our periodic table. We go 1s2, then we go through the 2s, and it's completely filled. We cross this divide. We're still in the second row, so we're still in the second energy level, but now we've entered the p block. Boron's the first element in this p block, so it would have 1 p electron. So boron would be 1s2, 2s2, 2p1. Let's see if you're getting the hang of it. Let's skip ahead, but let's not skip ahead too dramatically. Let's just take a look at nitrogen. Nitrogen is, better yet, we can take a look at oxygen. Let's really skip. Let's take a look at oxygen right there. Oxygen has 8 electrons, so we need to read to oxygen like we're reading a book. To get to oxygen, we read through the first row, so we're reading through the 1s and it's completely filled. Then we come to the 2s, and it's completely filled. Then we're into the 2p, because we're in the second row, p block. How many into the p block is oxygen? 1, 2, 3, 4. If we start counting at the beginning of the block, oxygen is the 4th element in that p block, so it's going to have 4 electrons in the 2p. The great thing about electron configurations is they're self-checking. We said that oxygen had 8 electrons. Right? 8 electrons. Therefore, if we've done it right, if we add up our superscripts here, if we add up these superscripts, they should equal to 8. Well, 2 plus 2 is 4, plus 4 is 8. So we've done it correctly. Now, we don't have to go through this long, laborious method to do all this if we don't want to. We can do it a much faster and easier way. Let's really skip. Let's skip down to sulfur now. Sulfur's right there. It's 16 electrons. We're going to have to read to get to sulfur. So we know we're going to go through the first row. So we know, whoops, that wasn't helpful. I want to leave oxygen there, so let's... Anybody seasick yet? Sulfur. We're going to read to it. So read 1s. It's completely filled. Then we go to the 2s here. So 2s2. Then we go all the way through that p block. So the p block has 1, 2, 3, 4, 5, 6. Remember, the p can hold 6. So the 2p is completely filled. We're still not to sulfur yet. So now we're in the third row in the s block. 3s, and it's completely filled, so it has 2 electrons. Then we come across the divide here to the 3p. So it's 3p, then 1, 2, 3, 4. So 3p4. Ta-da! And that's sulfur, and we can check and see if we've done it right. We can say 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16, which is what sulfur should add up to. Now, another thing worth pointing out is, where are sulfur and oxygen on the periodic table? Sulfur and oxygen are right above and below each other. And look at their last filled sublevel. For oxygen is the 2p with 4 electrons in it, and sulfur is right below oxygen. What's its electron configuration? It's 3p, 4 as well. So what that means is we can really begin to view these blocks on the periodic table as almost coordinates for electrons. Sorry, I'm cleaning up here, and I know that's probably, you're saying, hurry up, hurry up. What we can do is we can begin to view these now as coordinate blocks. We can say that anything in this column here is going to have 1s1. Anything in this column here is going to have s2. Anything in this column, p1, p2, p3, p4, p5, and p6. And because the row number equals the energy level, we know the valence configuration of these electrons. We know what those blocks represent. In other words, the outermost electron for lithium is 2s1, 2s1. For beryllium, S2, second row, 2s2. We come over here. Fluorine is the second row, 2, so for the energy level, for its outermost electron. And it's in the p5, so it's going to have 5 electrons in its p sublevel. So by its position on the periodic chart, for every element, we know its outermost occupied sublevel and the number of electrons in that sublevel. if we finished out this column here, 3p5, 4p5. Iodine would have its outermost sublevel filled would be the 5p, and it would have 5 electrons. And we could do this for any column over here. Let's do this one. 3p2, 4p2, 5p2, 6p2. All right, so you can see how this periodic table is providing us with information. All we have to be able to do is to read it like a book to figure out the electron configuration for any element. Before we do anything else, let's have you write down the word Candyland. Write down Candyland. C-A-N-D-Y-L-A-N-D, Candyland. Let's look at another example. And this example is going to set the groundwork for a very important concept that we want to understand and look at. Let's take a look at neon. Neon is right here. It's in the second row, and it's in column 8A. If we look at neon, to get to neon we have to read through our periodic table, so we're going to go through the first energy level. Both the elements in the first energy level are in the S block, so our S block is completely filled. Then we come to our second level, we go through the S, so we've got the 2S completely filled, and these 0 things here are my S's, cursive S. Then we come to the P block, so we go through the 2p, and it's completely filled, 1, 2, 3, 4, 5, 6. So that's the electron configuration of neon. If we move down to argon, argon's in the third energy level, and it's at the end of that P block right there again. So it's going to be 1s, 2, 2s, 2, 2p, 6. Then we come to the third row, 3s2, 3p, 6 again. What do you notice about both argon and neon? In both argon and neon, their outermost energy level has their S and P completely filled. That trend is going to hold for everybody in group 8A. All the elements in this have what are known as their valence shell completely filled. So what is the valence shell? The valence shell is the outermost occupied energy level in an atom. If we're to look at our friend neon, we said it had an electron configuration of 1s2, 2s2, 2p6. Its outermost occupied energy level is the second energy level. So we would say that neon's valence shell is the second energy level. And we would say that neon has 6 valence electrons. a similar and not only that, but as long as we're defining valence electrons, let's define core electrons as well. Core electrons are those electrons, basically, that aren't valence electrons. Core electrons are electrons in the inner energy levels. They're ones that are not chemically active. So if we were to look at neon, the core electrons for neon would be the 1s electrons. Those are the electrons that aren't going to participate in the chemistry of neon. Let's take a look at another example from our last slide here. What's a pirate's favorite element? Argon! So let's take a look at it for our next example. We did its electron configuration on the last slide there. So that's the electron configuration of argon. Its valence shell is the third energy level because that's the highest energy level in which it has electrons. Its core electrons would be all the electrons occupying the first and second energy level. We would say that argon has 8 valence electrons because 2 plus 6 is 8. The reason we're spending the time to talk about this concept of valence and core electrons is because at this point is because it can help us with our electron configuration. And by help, I mean it can make our lives a lot easier. Let's go back to our periodic chart. Sticking with argon here as our example, to write the electron configuration, I have to write all these core electrons before I get to my valence electrons. What's even worse, if you read that last slide, what do I say about core electrons? They don't do anything chemically. In other words, they're boring. They never go out and meet people. They never have a good time. They just sit there and watch everybody else react. They're the ultimate couch potatoes of the chemistry world. Therefore, why are we wasting our time writing them when they don't do anything? Good question. We shouldn't be. If you look at these noble gases, and let me line up neon right below argon, these noble gases, and remember noble gases are the term for group 8A elements, all the elements in group 8A have their valence shell completely filled. They have their valence S&P completely filled. So all those noble gases have their valence S&P completely filled. And therefore, what we like to do is we like to use noble gases to represent the electron configuration of electron cores. In English, noble gases, or elements in group 8A, in staple brackets, can be used to represent their electron configuration. For example, if we zoom here into our argon neon example, if we look at neon's core electrons, The core electrons of neon have the same electron configuration as neon does entirely. So to save ourselves a lot of work, when we write the electron configuration of argon, what we can do is we can write the elemental symbol for neon in staple brackets, and then just read our periodic table like a book. So here's argon, what we want to write the electron configuration of. What we do is we go to the line above, locate the noble gas, and then read our periodic table like a book. So I have neon, then I'm in the third row, S block, so 3s, then I'm in the P block, and 1, 2, 3, 4, 5, 6 into the P block. So I can rewrite my electron configuration for argon as neon, staple bracket, 3s2, 3p6. And in this, what's known as noble gas notation, what I've done is I've condensed all my core electrons that I don't care about into the elemental symbol for my noble gas. And I've only displayed and bothered to write those valence electrons, which are what I really care about. Let's look at another example. All right, let's do another electron configuration. Let's do it for phosphorus this time. Here's phosphorus on the periodic table. If we want to do its electron configuration using noble gas notation, the first thing we would do is we'd come up and find the preceding noble gas. So what's the noble gas before phosphorus? Neon. So I'm going to write the elemental symbol for neon in staple bracket. Now I'm going to read my periodic table like a book to get to phosphorus. So I start here at neon, and I'm coming to my 1, 2, third energy level. So I'm going through my 3s because this is my S block. So 3s, and it's completely filled, so 3s2. Then I'm into my 3p right here, starts my 3p. And to get to phosphorus, I have to go 1, 2, 3 into it. So I have 3p3 for phosphorus. If I hadn't used my noble gas notation, I'd have to start all the way back at my beginning of my periodic table and read down to phosphorus. 1s2, 2s2, 2p6, 3s2, 3p3. So I can eliminate having to write all of that stuff by using neon. Let's look at another example. Let's take a look this time at oxygen. I know we've done oxygen before, but we've not done it with a noble gas notation. And this is why, let's look at oxygen here. We have oxygen. The preceding noble gas for oxygen is helium. And this is why helium belongs 2 places on the periodic table. We said that electron configuration-wise, helium is 1s2. Electron configuration-wise, it belongs there. But chemical property-wise, and in terms of having its valence shell completely filled, 1s2 can only hold 2 electrons, so it's completely filled, helium belongs with the noble gases. So if we look at oxygen, we go to the preceding noble gas, it's helium. So we put its elemental symbol in staple brackets. Then we read our periodic table like a book. We're at the second energy level, so that's the S block. It's completely filled. 2s. Then we come to the 2p, 2p, and then 1, 2, 3, 4. 4 electrons in, and we have our electron configuration for oxygen. Chemistry's easy, life is hard, right? Let's kick it up a notch and give you something to crow about. Caca. Calcium. All the way down here. If we were to write it by hand, calcium would take us forever. But instead, we can go to the preceding noble gas, and the noble gas before calcium is argon. So we can write the elemental symbol for argon in staple brackets. Then we read our periodic table like a book. This is the, this is the fourth energy level, S block, and we're 2 elements into it. So argon 4s2 would be a shorthand way of writing the electron configuration of calcium. Let's do a couple more examples just to make sure this horse is thoroughly dead. What I would like you to do is I'd like you to try to write the electron configuration of silicon all by yourself. Everybody try to do the electron configuration of silicon all by yourself. So pause me, try it. Raise your hand if you didn't pause me. Yeah, I know you didn't. You got things to do. You want to hurry up. Oh, wait a second. That's being rude of me. I know that you alone are the one who did pause me and did the example. It was your classmates who didn't, but, you know, we won't talk bad. All right, let's go. We got silicon right here on our periodic table. The preceding noble gas to silicon is neon. So we read our periodic table like a book. 1, 2, 3. 3s is full. 3s2. Then we come to the 3p over here because this is the third energy level, p block. And silicon is 1, 2 into it. So 3p2. Chemistry's easy, life is hard, yes? Let's make sure it remains easy for you. And let's do lithium. Again, I wouldn't hurt to pause. But all right, the preceding noble gas to lithium is helium. Then we're at the second energy level, S block, and lithium's the first element in it, so it's only 1 electron there. And that's the electron configuration for lithium. Chemistry's easy, life is hard, right? These are practically free questions on an exam. I am giving you all the points you could ever want. Let's do one more just to make sure we're all on the same page. If we do potassium, right here, the preceding noble gas is argon. It's in the 1, 2, 3, 4th energy level, and it's in the S block, and it's the first element in it, so it would be argon 4s1. Chemistry's easy, life is hard. You won't be sorry you took the class, so why don't you write down sorry? The game sorry, S-O-R-R-Y, sorry. Let's kick things up a notch and introduce something that we haven't touched before. Up till now, we've rigorously not done any of the elements that aren't main group elements. Matter of fact, we haven't done any of the elements beyond calcium. So we've kept all our elements 20 or under. Let's be bold. Let's go and do the electron configuration of titanium. Titanium is right here. It is right there. So let's go and find the preceding noble gas to titanium. And the preceding noble gas to titanium is argon. Then, because we're in the 4th row, titanium's in the 4th row here. 1, 2, 3, 4. We come to the 4s. This is the S block. So 4s2. Then we count over 1, 2, and we've entered the D block. And titanium's the second element in it. So it's going to have 2 electrons in the D. The question is, what number belongs here? It turns out that, remember, that the 1 has an S, the 2 has an S and P, and the 3 has an S, P, and D. If we look at our periodic chart, and we look at our third row, 1, 2, 3, where's 3D, right? This is the third row, and this is the D block. And we know that the 3D exists, or at least that's what I told you. Where is it? It turns out that there's an energy overlap. There is an energy overlap such that it is cheaper, i.e. costs less energy, for an electron to live in an S of a higher energy level than it does for it to live in the D of a lower energy level. It's less energy to occupy an ns orbital than it is to occupy the n-1d orbital. In other words, the 4s has less energy than the 3d, and that overlap trend continues. It takes less energy to live in the 5s than it does to live in the 4d. It's less energy to live in the 6s than it is to live in the 5d. I like to use a Simpsons analogy to help explain this. If you watch The Simpsons, you know that there's a neighboring town to Springfield, Shelbyville, that is the wealthier town. And the property values in Shelbyville are higher than the property values in Springfield on average. However, it's cheaper to live in the bad neighborhood of Shelbyville than it is to live in the gated community of Springfield. Right? By the way, interesting side note, with the state that Springfield is located in on The Simpsons varies depending on who the chief writer of the show was at the time. The creator intended Springfield to be in Oregon. But, however, there was a native Kentuckian running the show for a period of 3 years. And for those 3 years of the run, they will make several locations to Springfield, actually being Springfield, Kentucky, such as drive south to Tennessee, drive north to Indiana. Just a side note. And that Oregon and Kentucky both have Springfields and Shelbyvilles. But I digress. What this overlap means is that electrons will go into the 4s before they go into the 3d, they'll go into the 5s before they go into the 4d, the 6s before they go into the 5d, so forth and so on. So what we have to do is we have to modify our mnemonic devices for our periodic chart. Matter of fact, I'm going to draw my own hand-drawn one here. Really, Dr. Kelly, you're going to go hand-drawn? Yes, I am, because I'm a budding artist here. For your S blocks, the energy level is the row number. For the D block, the energy level associated with the D block is row number minus 1. Then we come over here to the P block, and it's back to being the row number. We haven't talked about the F block. Turns out an energy overlap exists for the F block as well. The F block is actually going to be row number minus 2. This isn't just a gated community, this is where you own the whole subdivision. So the F block has a row number -2. And you can see that in pretty colors here in the figure that the book's provided. S2SP, 3S, 3P, 4S, then we enter the D block, and because we're in the 1, 2, 3, 4th row, that's the 3D. Then you come to the 4P. 5S, 5th row, the D block would be the 4D. Then we come to the 5P. And here's where the energy overlap gets really cool. After the 6S, you go down and fill the 4F. Right? It's cheaper for electrons to live in all of these energy levels before they can live in the 4F. And after the 4F is filled, then you go back up and fill that 5D. It's not bad when you look at it in terms of atomic number trend. The atomic numbers actually tell you where to make those switches. If you see 19, 20, 21, so we know we're going to keep going into the 3D. If we leap ahead here, we're in the 1, 2, 3, 4, 5, 6th row. And that's cesium at 55. Then we go 56. And then where's 57? Down here, right? So you can see you're going from the 6S to the 4F. And then you go 57, 58, 59, 70, and then we're 71, right here, where it's the 5D, because we're in the 6th row, D block, so row number -1. So 4S, 3D, then we're in the P block, so it's row number again, 4P, 5S, 4D, 5P, 6S, then to the 4F, then to the 5D, then we're back in a P block again, so it's 6P, then 7S, and then from the 7S we go to the 5F, 89, 90, 102, right, 88 to 89, then 102 to 103, so it's row number -1, so this must be the 6D, and then 7P are either undiscovered or artificial. So what does that have to do with titanium again? Where were we on titanium? I don't know. Titanium Man got bored sitting around and went out to find Iron Man. All right. We've got argon as the preceding noble gas. Then we come to the 4S, and it's completely occupied, so 4S2. Then we're in here, and this is the 3D. And we're the 1, 2 into it. 3D2. So that's the electron configuration of argon, of titanium. One last cleanup note that I find incredibly annoying. Your book kind of differs from how other places do it, so you may have to be aware of how Mastering Chemistry is going to do it. And let's do this on another slide here. All right. Let's do another example. Let's really kick things up a notch, and let's do namibium. Right here, 41. So I write my elemental symbol for namibium. Then I find the preceding noble gas. The preceding noble gas right there is krypton. So I'm going to write the elemental symbol for krypton in staple brackets. Then I'm going to read my periodic table like a book. 1, 2, 3, 4, 5. So I'm in the 5th row, and this is the 5S. This is the 5S. It's completely filled, 5S2. Then I come to this row here, and that's the D block, and D block is always row number -1. So that means it's the 4D, and I'm 1, 2, 3 elements into it, so that means I've got 4D3. I would also note that the chart in your book is wrong there, that's actually a mistake on the part of your textbook, that I'm actually right there for namibium. Now, it looks like they've got other mistakes there, but they're not mistakes. The other things are right, and we'll talk about them in a second. But at the moment, your book's wrong there on nimibium. That's nimibium right there. All right, let's take a look at let's take a look at another example here. Let's do, let's do cobalt. Cobalt's right there. So we find the preceding noble gas to cobalt. That's argon. So we write the elemental symbol for argon in staple brackets. Then we come to the 4s, and it's completely filled, so 4s2. Then we're in the D block, and D block is row number -1, so it's 3D. And we count over to cobalt. 1, 2, 3, 4, 5, 6, 7. So 4s2, 3d7. Chemistry's easy, life is hard. Let's take a look at another example or two. Let's do bromine. Ta-da! Right there. So find the preceding noble gas. Step 1, preceding noble gas is argon. Then we're going to read like a book. 1, 2, 3, 4. So we're in the 4th row for bromine. So first we come to the 4s, and it's completely filled. So 4s2. Then what's this? This is the 3d. The 3d is completely filled because we're not yet to bromine. Remember, the d holds 10 electrons. You can also remember because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there, right? So 3D is completely filled, 3D10. Then we're back into the P block. And therefore it's back to being row number, not row number -1. So it's the 4P. And it's 1, 2, 3, 4, 5. 5 into that P block. So it's argon 4s2, 3d10, 4p5. Chemistry is easy, life is hard. Just because I want to make sure this horse is dead, ridden into the ground and ready for the glue factory, let's take a look at somebody who's going to obey me. Let's go promethium. I kind of liked promethium. I don't know how anybody else did. I thought it was a worthy prequel to Aliens. But I digress. So we've got PR right down here. Here's the tricky part. What's the preceding noble gas? To do that, we really have to count backwards. We're at 59, 58, 57. Where's 56? Right there. 56, 55, 54. So xenons are preceding noble gas. So now we want to read to xenon until we get to promethium. Xenon, then comes this group, and this group is 5, 6, so it's the 6s, and is completely filled. 1, 2, 6s2. Then we come down here, and F block is row number -2. So this is the 4F. And promethium is 1, 2, 3 into it. So xenon 6s2, 4f3. Write down Monopoly. Write down Monopoly. Write down Monopoly. I hope everybody wrote down Monopoly. M-O-N-O-P-O-L-Y.